All right, cool. I think we can begin. If people trickle in, then hopefully everyone will catch up. Can I get a raise of hands of who has been here who's been at a previous AI club meeting this quarter? Just wanna get a sense of where everyone's at. Okay. Um, how confident do you feel your abilities are in neural networks? Just from the very beginner. Do you understand the concept of layers? Because that's really all that is necessary for this one. All right, cool. Hopefully you should be set. If you have questions, which I kind of expect all of you guys to have questions, please raise your hand. This is just going to be an introduction to transfer learning, as it can get very complicated very fast. So this should just be a lot of pictures. Shouldn't be too difficult. All right, cool. Let's get into it. So I like to start off just with a quick challenge for you guys. If you were given a task of taking a bunch of images and to classify those images as a specific dog species, what would be your guys's first steps? Or what kind of model would you build? What would you think? Just anything, any ideas that you guys have for maybe a problem that looks like this? Yep, you could train a model from scratch. In your case, a convolutional networks tend to be very good with image data, which we talked about earlier. I think it was because of it doesn't look at positioning as much as neural networks. Spatial position, right? For the most part. But that is a completely fine assumption to make for this, and it works out pretty well usually. However, there is a couple issues with building a model from scratch. One is, how exactly do we start building a model from scratch? Well, there's a lot of different things we have to figure out. Okay, how big exactly do we want our model? Yes, we've decided convolutional, but do we want to try out other things as well? There's a lot of different things that we'd have to play around and figure out if you want to build a model from scratch. Additionally, if you want to build our model from scratch, we need a lot of data. You train a model, I'm sure if you guys have experience with this, you need a data set, and it needs to be especially large if you're doing a difficult task. While getting a bunch of photos of dogs might be fun to look at, it's going to be very tedious to get all the different pieces of data and also make sure that they all work for your model. Oftentimes you'll need images that are all of the same size, the same dimensionality. So for instance, the RGB channels all have to be the same. And so oftentimes that can be a lot of work to get a lot of data, whether or not that's even feasible. In this task, it shouldn't be too hard to get a bunch of pictures of dogs. But you can see how this can easily get out of scope. Another thing is this could be very computationally expensive. When you do work with a lot of data, you have to work with more extensive models. Sometimes they can be simpler, but oftentimes they can be a lot more complex. And this means it takes a lot of time to run these models. And it can also mean more expensive hardware, such as anyways, it could get very costly if you're trying to train a model from scratch, especially more complicated models that look at image data. So what can we do to kind of ease some of these things? Well, if we want to, we can actually build off an existing model. And this is kind of what we'll be talking a lot about today. So for instance, there is a data set or challenge called ImageNet, which is just a million images, I think, to train on. Your goal is to classify those images into a bunch of different objects. As we see here, you can classify into mammals all the way up to working dogs or huskies. And taking this really complex model that may be pre-trained for this, so something that the likes of Google or Microsoft has trained with however millions of dollars they've spent pouring into that. Take that model and just use that as a starting point. And if we use a existing model starting point, that means we don't need to use as much training data as it already has some concepts learned, which we'll go into a little bit later on. Additionally, because we are not training from scratch anymore, we're starting with this existing model as a base, it results in faster training times. And this together is called transfer learning, which we'll see is because we're transferring learning from one model into a new model that we have specialized. So, like I mentioned, transfer learning as a whole. So if you take anything out of this presentation, just know that transfer learning is repurposing an existing model for your own benefit or for a secondary task. So there's a quick overview as to what this may look like, transfer learning versus regular machine learning. I'll often use the word source and target as tasks or domains. Think of the source as what your original model is trying to do, or the task or data set, whereas the target is the goal of your second model. So if we did a more traditional machine learning approach, we'd have to build two completely unrelated systems, one on the source data set and one on the target data set. They have nothing to do with each other, even if they might be related to each other in some respect. On the other hand, transfer learning uses our source data set or our source domain to build a single classifier model, what have you. And you can use some of that information, whether it's all or part of it, which again, we'll go into a bit later, to transfer that information to a secondary or that target model, which uses that target data set or data set 2 here. Again, just a quick overview. Don't expect you to 100% get it yet, but you should have an okayish understanding about the concept of transfer learning, taking an existing model to build a secondary model or just improve upon. Cool. So when can we use transfer learning? So let's say we still have this problem of trying to classify a specific dog species. Well, let's say we had our source task or model being sentiment analysis. If you guys were to guess, would you think that this is a good source task or model for training a dog classification? Sentiment analysis. So that's given a sentence. Is it a positive sentence or a negative sentence? Can I get a raise of hands? Who thinks this is a good example? Yeah. Okay. What about who thinks it's a bad source task for predicting or classifying dogs? Okay. Yeah. You guys would be pretty straight on there, right? If we're trying to learn or transfer something from an original source task, there should be some sort of a relationship between your source task and your target task. Oftentimes, this is seen with similar domains. So for instance, if we look at this example, just generic image classification, they do have the same domain where they take in an image and they output some classification that's categorical, whether it's a string. I guess it doesn't really matter too much about the output type. As you see here, the domain is the same, and you could sort of see how classifying an image to, for instance, a dog, deer, frog, whatnot, is somewhat related to classifying a dog. So can you use transfer learning only if the source and target domains are the same? Actually, no. There's a lot of different ways you could do transfer learning. For complexity reasons, we will only cover when the source and target domains are the same. So for instance, classifying two images would be, or classifying an image as a dog versus classifying an image as whether it's an automobile or a human. Those are same domains. Whereas classifying an image versus classifying text would be different domains. If you really care about, if you're learning more into transfer learning, there's a bunch of different topics that we can see in the tree as to how to do different types of transfer learning, such as transductive transfer learning, unsupervised transfer learning. We'll be covering inductive transfer learning. This is where the source and target domains are the same. One thing to keep in mind when doing inductive transfer learning is while the domains have to be the same, the tasks can be different, but there should be some relationship. And the reason why it's called inductive transfer learning is because you should be able to inductively learn something from the source. So that's a definition of inductive, using a particular set of facts or ideas to form a general. So just trying to get some ideas from that source to then learn into the target task. Does anyone have any questions so far? I know it's been pretty high level information. How are we feeling? I get some thumbs up, thumbs down, thumbs down. Where we are going, because we will get a little bit more technical. Yes. The difference between transductive and inductive, deductive. I've never heard of deductive transfer. That's probably just some semantic. But also, if we look at the tree, inductive transfer learning is only when you have actual annotated data in a target domain, whereas Transductive transfer learning is annotate data only in the source domain, so it might be a little bit different definitions there. And I could probably look that up after as well. On what deductive. All right, cool. So some benefits of transfer learning. So I know I talked a little bit about this earlier, but kind of looking at this in a more rigorous scope. If we were to graph out our training sample as training over time and the performance of the models, that could be accuracy or whatever categorical performance objective that you want. In this case, there are three main things that we can benefit from transferring. So this is, you don't necessarily are given all three, but the goals have at least one of them. So the start might be a higher start. So this just means that when you start off with that model with those randomized weights, when you start off with an existing model, you kind of expect to have a little bit higher performance than just using a brand new model with randomized weights. So that might be a benefit of transfer learning. Another one is higher slope, or that the model, the transfer learning model, will learn at a faster rate than building something from scratch. As we can see in the picture, higher slopes kind of gains performance in a faster way than training. So maybe takes less epochs to fully train than does one from a brand new higher asymptote, increased upper limit of performance. So once all your variables have converged and the weights have stopped changing, hopefully when you do transfer learning, you will have a higher performance once all the weights have converged after backpropagation training. Those are the three main goals that we have from transfer learning. One, can we start at a higher initial performance? Two, can we learn faster? And three, can we get to a higher converged performance? So if we remember in some previous workshops that we've had, neural networks, each layer kind of represents different things. These are the hierarchical feature representations. If we were to look at this model here, for instance, we could see that maybe the first hidden layer can identify vertical lines, horizontal, just to see just generic geometric shapes. Whereas by the time we get to our second layer, we can then combine the knowledge of these geometrical shapes into features or objects that we might be able to identify, such as we see some noses, some eyes, mouths, things that maybe make a little bit more sense when we kind of look at it in an abstract way. And finally, when we get to the third hidden layer, we can get to see faces. So this is learning from, hey, if there's a left eye, right eye, nose, and a mouth, then there's probably a face here, and that can be identified in the third hidden layer. So for instance, we could take this pre-trained model and those features, and we can extract those. So one thing we could do is we could just cut our neural network, just chop it off at one of the layers and say, hey, from here, we don't actually care about, let's say, predicting whether or not this person is of a certain race, gender, whatever have you trying to predict from these faces. Instead, I just want to get the features such as whether or not this is a picture of a nose, an eye, a mouth. So we can cut it off at around between hidden layer 2 and hidden layer 3. And we can then add our own maybe smaller model at the end here. So for instance, in this case, we have some convolutional layers that we're cutting off. And then once we have after our first fully connected layer, as we can see here, we then are able to build off of that previously trained model with a SVM, support vector machine. It's just a smaller class for that. We'll get into, I think, the next quarter is when we touch into SVM. Oh, next couple of weeks we'll talk. It's cool. And so you can then take the new data from that we're looking at. So for instance, images of noses, mouth, ears, to build our new model from the original pre-trained. Does anyone have any questions about how we can use a pre-trained model as a feature extractor? Basically chopping it off and building, adding on a smaller, maybe shallow model like the SVM to then retrain a little bit to get those features rather than taking in whatever that final goal is from the previous example. How do we feel about that one? Yeah, thumbs up, middle, down with that one. I know we're getting a little bit more into it. All right, cool. Well, we'll go into the next one. We'll see if you can backtrack if you have any more questions from there. So now instead of using a pre-trained model as a feature extractor, let's talk about fine-tuning pre-trained models. Without, I guess, looking up here, who here has heard of fine-tuning? as a concept. Who here would like to take a guess as to what fine tuning is? Yeah, go ahead. Mhm. Exactly. You have an existing model, and all we're doing is we're giving it new data, maybe something specialized for the task, and seeing if we can modify the weights just a little bit, not like completely change everything, so that our original model is now works a little bit better for the new task. And this is what we could do in transfer learning. Example of what we could it's an example of transfer learning. There's kind of two main parts of fine tuning. There is freezing and the fine tuning layer. So when we look at an existing model, we realize that, hey, we don't necessarily want to be changing the weights of the entire model. So for instance, if we looked back at our uh, face classifier, if we're building something that wants to also kind of look at faces, we still kind of want the geometry plus maybe these features. Instead, all we really want to do is kind of change that last layer to predict what's an good example of something that we can do that's related to faces. Emotion, yeah, maybe originally it was training on the gender. Now we want to look at emotion. When we look at emotion, we still want to identify information based on the eyes and the mouth. And so because of that, we want to keep the features from the hidden layer 1 and 2 intact. We don't want to change it. Instead, all we want to do is modify that last hidden layer. And so we could do that by freezing those first couple of layers, meaning that when we go to retrain it in the fine tuning stage, which we'll get to in a second, those weights and values do not get trained or do not get updated during the back propagation step. And so this allows the information that gets learned from those initial layers to be transferred from the original model into our new modified. And finally, we have our fine tuning or our final layers that we would like the weights to be updated. So given the pre-trained notion of features such as the face and the eyes, how can we use that to then learn emotion? So that's where we just change the last couple of layers to hopefully be able to be better predicting your facial and your emotions from different facial features. I think that's it for the fine tuning. Yeah, does anyone have any questions about the concept of fine tuning or learning from an existing? How do we feel about this? Thumbs up, middle, down. Some middle, some middle. Okay. This can get extremely complicated if we go a little bit deeper. So the slides are just gonna be a quick introduction. I think the next one's our final slide that we have, which is about the challenges of transferring. I know I skipped on these a lot, but knowing about when, what, and how to do transfer is extremely difficult and is definitely out of the scope of kind of an introductory lesson what transforming is. There are plenty of research papers and ongoing research as to how to identify when we can use transfer learning or even what tasks can be inductively learned from other tasks. A lot of that turns out to be trial and error, plus I guess a little bit of experience helps as well there, but there's a lot of algorithmic jargon that you don't even know. One big issue with transfer learning is the concept of negative transfer, which quite literally means learning negatively. So, for instance, if we took an existing model that classifies, let's say, the different objects, dogs, cats, and use that to classify the type of dog, maybe by using transfer learning, all of a sudden our model has gotten worse. In that case, that's called negative transfer, which is obviously very bad and can often be a cause of a shift between the source and target task, or simply the fact that to induce the from that source task. Again, whether to how to know when you can or not cannot is kind of hard. Kind of, I guess a good rule of thumb is use transfer learning if a task is a subset of another task. So, like I mentioned with predicting the breeds of dogs, if you had a model that could classify a dog to begin with, that might be a good step or a good source task for transfer. And finally, another thing that there's a lot of research going on is transfer bounds or the quantification of the knowledge as identifying, okay, what information is actually being transferred from the source model to that target model is really hard to identify. It's very black boxy as we have. I think that's it for the slides before we go into the notebook. Does anyone have any other questions as we go on to the notebooks? I'm sure there'll be more questions on how everything works. But yeah, I think that's it for the slides. These are really quick. I don't want to go too in depth into the mathematics or the different transfer learning algorithms. But yeah, if everyone can, we have our book here /Sky Transfer Learning. If you can, once you open up that notebook, make sure to make a copy of it so when you make your changes, it actually gets saved. I'll give it over to you.
Alrighty. I'm going to stop the recording in a moment because the people in the figure it themselves.